So welcome to the next edition of the Economic Geology of Lunar and Asteroid Resources. We're lucky today to have Dr. Brett Denevi from the Applied Physics Lab to talk to us about the Lunar Highlands. Brett is quite an accomplished scientist, the Deputy Principal Investigator for the Lunar Reconnaissance Orbiter, the co-investigator on ShadowCam, which will be an instrument to image the permanently shadowed regions of the moon from the Korean Pathfinder lander. She's already Vice Chair of LEAGUE and has served as the Deputy Instrument Scientist on the Mercury Dual Imaging System on MESSENGER. So she has a NASA Early Career Fellowship, 7 Group Achievement Awards from NASA, and an asteroid, 9026. Denevi is named in her honor. So I'm really looking forward to learning a lot more about the Lunar Highlands, and I want to turn it over to Brett in just a moment. I will remind people of the ground rules. If you have questions, please put them in the chat box, and I will interrupt our speaker to ask those questions. People around this table are encouraged to ask questions as we go along. The one open mic will be here at UCF. And without further ado, Brett, take it away.
All right, thank you so much. Yeah, this is a really fun class, and I just want to emphasize too, I love answering questions. So, please, if something's unclear or you're just interested in hearing more, just, definitely feel free to interrupt or write in the chat box or whatever. I can't see the chat, so right now with the full screen, so I guess that's okay. You'll just announce, Dan, the chat questions you said.
Yeah, I'll monitor the chat box and let you know and read you the question.
Okay, super. So I think that you guys have already talked about, kind of the basics of the lunar magma ocean, I guess last week and things. But since we're talking about the Lunar Highlands, I'm just going to, hopefully this video is coming through okay, to show the kind of basic scenario here where you have your basic minerals, the iron, magnesium bearing, olivines and spirituals first, sinking, and then our heavy, our lighter aluminum-rich plagioclase, the little white dots that are floating to the surface here, that makes up our highland crust. So I assume that I saw David Pring talked last week, so hopefully that we're all on the same page with the basics here. And so once you have that scenario complete, we're on to the Lunar Highlands, which are essentially composed of the flotation crust from that global magma ocean. And so the topic that I was told we were going to talk about today was the post-magma ocean evolution of the Lunar Highlands. So that's really all I'm going to say about the magma ocean. So the specific topics in terms of the post-magma ocean evolution, we'll talk about the highland crust in terms of the mineralogy, the rock types, and then really a lot of what the highlands is the study of the regolith. So we'll talk about the definition of the regolith, how it's produced, crater saturation, mixing in the regolith, and then a bit at the end about what the highlands are like at the lunar poles. So of course, when we're familiar with looking at the near side, we see so much of it is covered with mare, but the lunar mare are only around 18% of the moon's surface. So the vast majority is the lunar highlands. And when we go through and look at a couple of different global data sets, you can see the highlands are just physically higher. This is topography. Most of the lunar highlands are substantially higher in elevation than the lunar mare. They are iron poor. This is the iron map from the Clementine data set. Iron was derived by Paul Lucy. And so you can see most of the highlands are pretty iron poor. Titanium as well, very much just concentrated in the near side lunar maria, a bit in some of the volcanic deposits on the far side maria as well. And then we get to thorium. Thorium, the heat-producing element, very strongly concentrated on the near side, apart from a couple exposures on the far side. And so in 2000, after most of these data sets were collected, Brad Jolliffe did a really great job of breaking the moon out into the three major terrains. This was not just the Mare and the Highlands as kind of classically defined, but once we had this chemical data, you could see that there were actually three terrains. So of course, the feldspathic Highlands terrain, really defined by about 4 to 6 weight% iron, very low iron, just reflecting that high plagioclase content. And then the low thorium, consistent with these flotation crust from liquid crystal fractionation. Then there was also the Procolarum creep terrain. This was not recognized necessarily early on, but once we had these global remote sensing data sets, we could see that thorium in particular, and along with titanium and other elements, were concentrated within this one portion of the lunar near side. Have you guys already talked about creep?
A little bit, just mentioning that it's there.
Okay. Well, I'll just give the Cliff Notes versions of creep too. So creep is the potassium, rare earth element, and phosphorus terrain. Somebody came up with the great acronym. I don't know whoever did that. Fantastic. But so creep is also kind of a product of the global magma ocean, where the Highlands flotation crust formed, and then the mantle, the more iron-rich cumulates that sunk, and basically everything that was left over, all of these elements, potassium, the rare earth elements, that are kind of incompatible. They don't get readily incorporated into minerals. They were just left over as this kind of last sludge of the magma ocean. And so those are really located right, typically below the Highlands crust and above the mantle. So this kind of thin layer of incompatible stuff. Titanium is another one, why there's so much there. It's interesting that the creep is so asymmetric. If this is really part of a global magma ocean, why is it so concentrated just on the near side and only really a portion of the near side? And then the third terrain that we talk about is the South Pole Aitken Basin. It has a higher iron content than the typical Lunar Highlands, moderate thorium, and the fact that this was this enormous basin that dug deep down into the crust, potentially excavating some of the mantle, and there's still not a lot of this creep within the basin, really suggests that there is, a really fundamental asymmetry in terms of how these rare earth elements, potassium, are distributed across the moon. And that is something that we still don't, understand. Why, how we have this big asymmetry.
Are there any prevailing theories about the asymmetry or current modes of studying that?
There are theories, yes. I think we don't necessarily have any really good testable hypotheses for the asymmetry. Of course, giant early impact is always an answer for global asymmetries, but it would have to have been extremely early on, and we don't really see any evidence for that in the GRAIL data sets. There's ideas about, well, the moon was closer to the Earth, and so there's some kind of tidal differences on the near side, but I don't know how that would concentrate creep on one side of the moon versus the other, but yeah, there's no really great answer for that. Here we go. All right. So, oh, I see our delayed reaction here. So the interesting, thing is that so much of what we learned about the moon early on was coming from the samples, and these are all the different sample sites. And you can tell from what we've just been looking at with these global maps that they are not really representative of the moon as a whole. They're, really strongly affected by this Procolarum creep terrain. So it really has taken some of the remote sensing data sets as well as meteorites, which we'll talk about a bit, to kind of get this global picture. But it is remarkable what you learn, what we did learn from each of the landing sites in terms of the highlands. So I was just going to go through some of the important notes for what we got from the different Apollo samples, specifically for the Lunar Highlands. So the Apollo 11 landing site was in Mare Tranquillitatis. I love these old images. You can see the arrow here pointing to Apollo 11 landing site. And of course, this is a Mare location. It was around 40 kilometers from the nearest highlands. But still, there was enough bits of anorthosite within the regolith and some of the regolith breccias that the entire magma ocean hypothesis was developed just from these tiny fragments of anorthosite found in this Mare site. And so I've included here a picture of the regolith that I've taken in the lab here. I think this is actually Apollo 12, but you get the same idea. I've sieved this sample to 125 to 250 microns. So for scale, all of the particles here are, in this hundreds of micron size range. And you can start to get an impression of how this magma ocean hypothesis could have been developed from a Mare site. Apollo 12 is also a Mare site. But in this sample, you see all these wild bits of material from all across the moon, really. Can you see my cursor, hopefully? But so most of these bits are lithic fragments from Mare basalts or little weathered pieces that are impact glasses. But there are some fragments in here, mostly the little white pieces, that are anorthosite. In this case, a lot of the highlands material at the Apollo 12 site was transported mostly by nearby impact craters. At the Apollo 14 landing site, you can see the arrow up here at the top. This was really the first mission to land in the rugged terrain of the moon, so the highlands. It was landed on the Frau Mauro Formation, essentially ejecta from the Imbrium Basin up to the north. And you can even kind of see some of that scouring pattern across the site that looks like it's pointing back toward the Imbrium Basin. But here, this is not our typical highlands, what we would expect for most of what the far side is made of, or the polar regions. This is still part of this Procolarum creep terrain. So a lot of the samples from this site were not anorthosites. They were these kinds of more strange evolved lithologies and a bit more iron-rich. The Apollo 15 site, this was actually landed at the edge of Mare Imbrium, so within the Imbrium Basin, and close to the Apennine Mountains. The Apennine Mountains are one of the massifs, that's the mountain range that makes up the rim of the Imbrium Basin. And so this is a really complex site, but because it was right on the edge of Mare and some highlands material, the samples that came back were a lot of anorthosites, and this was really the first anorthosite collected directly from the highlands, so our first real chunk of the highlands crust. And you can see what is known as the Genesis rock 15415, they were looking for that oldest piece of the lunar crust to really confirm this magma ocean and understand the dates, the earliest timing of the formation of the moon's crust. There's also a variety of different more evolved lithologies that are found as just little pieces and clasts within the regolith and within breccias. And I'll go through those different types of rocks in some detail. Not exhaustive detail, but in some detail. And then the Apollo 16 landing site. This is really when, if you want a highland sample, what our best samples that we have are really from the Apollo 16 landing site. And this is the Descartes Highlands. So this area, you can see here where the Apollo 16 landing was, right in this kind of smooth area in between the more rugged Descartes Highlands. The smooth area was the Cayley Plains. This site is famously targeted because it was thought that this was going to be some kind of unusual highlands volcanism. You can see, hopefully, even just in this image here, that the site has a kind of higher albedo compared to up here, the Mare. So they thought, oh, these, they're similar, flat, smooth regions. This must have formed in a similar way through volcanism, but be some unusual composition. And when they did collect the rocks, even when the astronauts were on the surface, they knew right away that these were not volcanic rocks. These were impact breccias, a mix of rocks that were, again, ejecta from the Imbrium Basin, mixed with a lot of local material. So in this area, there were a lot of anorthosites. This is the just general regolith in this area is our most typical low iron highland samples that we do have. So when we look at where these came from, again, we're getting a small piece of the near side. Is someone asking a question? We're trying to.
Oh, I think that was just a mistake on.
Okay. Okay. So you can see we never really, just going back to the context, we never really did get super far away from, for example, the Imbrium Basin, which really affected a lot of the near side, and never really did get far away from this kind of unusual Procellarum creep terrain. Luckily, we do have the remote sensing data to get a handle on, much farther away regions. And then the other really valuable resource is the lunar meteorites that are really our best sample of. Some of them are likely from the far side, but of this feldspathic highlands terrain, because they are essentially just a random sampling of the moon's crust. So Randy Kortev curates this really excellent website about the lunar meteorites and keeps this updated. But the plot here is showing just iron weight percent. On the bottom, it's showing as it was derived from Clementine reflectance data. The middle is showing same thing, except just from lunar prospector data, gamma ray spectroscopy. And then on the top is the same histogram of the iron abundance in the lunar meteorites. So you can see a lot of them are from this very low iron feldspathic highlands terrain. And they are giving us our look at the highlands, some of our best looks in terms of what those samples are like, what the surface is like. So I don't want to get too far into the weeds on highlands rocks because, I'm a lunar scientist and there's very rare times that I have to understand the magnesium suite or evolved lithologies like the alkali suite. Most of the highlands is really our Pharoan anorthosites, but you might hear a lot of talk about the magnesium suite and these evolved lithologies. So I think it's worthwhile just going, going through those a bit without getting too far into the details. So this is a slide that I got from Carrie Donaldson-Hanna, who is now at UCF. She is the queen of plagioclase. She has really done a lot of work mapping out where we have the small variations in the composition of plagioclase on the moon. But this is our kind of standard ternary diagram for rock types that are most applicable to the moon. So at the top we have plagioclase, and then at the bottom left, pyroxene, and then bottom right, olivine. So at the very top of the pyramid here in red is anorthosite. Anthracite is just one of the types of plagioclase, and when you have over 90% anthracite, your rock is called an anorthosite. So this is the kind of end member composition for the moon. But a lot of the moon's surface is really more in these kind of pink and purple here. The noritic anorthosite usually, and then the anorthositic norite. So these are just kind of going down the left side of this ternary diagram here with increasing abundances of pyroxene. So you can see you're still well over 50% plagioclase or anthracite for much of these rock types. Much less common getting down here into the norite or gabbro. So most of the highlands is noritic, anorthosite, or anorthositic norite. I wanted to add to just the plagioclase diagram here, where geologists love these ternary diagrams. So we have potassium. These are all types of feldspars or of plagioclase. At the top we have the potassium-rich end member, orthoclase. Bottom left is albite, that's the sodium-rich end member. And then bottom right is anthracite, or calcium-rich end member. So on the moon, we're really strongly up here in this kind of anthracite range, so very calcium-rich pyroxenes. Most of the Earth is more down here, so kind of the highest AN numbers that you get in large abundances are, kind of the labradorite, bitumenite kinds of feldspars. So it is kind of rare to have this enormous, massive deposits of anthracite on the moon. This is a plot that I'll show because it is shown all the time and really kind of breaks up the three major types of highland rocks. So the x-axis is what I just described here as the AN number. It's the mole percent anthracite in plagioclase. So over here you can see it's just the calcium divided by the calcium, sodium, potassium in plagioclase. So when you have high AN numbers, you're up here in this really calcium-rich feldspars. And then the y-axis is the Mg number. That's the amount of magnesium over the magnesium plus iron in the mafic minerals. Actually, I don't know a ton of background about what everyone online and in the room is studying or has studied. So these mafic minerals are just the ones that are rich in iron and magnesium, and they're the pyroxenes, the olivines, whereas plagioclase is really this more calcium aluminum rich kind of rock. But the mafic mineralogy is more typical of what you find in the lunar mare. And then our plagioclase is, of course, dominating here. So if you plot all the samples, and they're not plotted here, it's just showing different fields where the samples fall, they break into these different groups. The Faroan anorthosites are the fans, the magnesium suite, and then the alkali suite. And so I think I have a whole slide, yeah. So the Faroan anorthosite suite, this is Most of it is, very plagioclase rich, over 85% plagioclase. So that's in that neritic anorthosite kind of range. Sometimes we have over 99, up to 99% plagioclase in these rocks, which is just really remarkable when you try to understand how you got such a pure plagioclase crust in some parts of the moon. They're called Faroan anorthosites because the Mg number in those mafic minerals is pretty low. And then, I've already talked about how these are rich in calcium. And then the ages of these rocks really confirm that the Faroan anorthosite suite is old, 4.4 to 4.56 billion years. These rocks are typically very beat up. They have been sitting on the moon for, over 4 billion years, so it does get very hard to date them. But we think they're around, this 4.5 billion years old, so dating that initial formation of the flotation crust of the magma ocean. And when we talk about the highlands, this is our main thing. The next two are smaller components. The magnesium suite, these are much more mafic. They're much more rich in pyroxene and olivine than the Faroan anorthosite suite. As their name implies, they have a higher Mg number, and you just have this really more diverse set of rocks. You have dunites that are really olivine rich, troctolites, olivine and plagioclase mixes, norites that are half calcium, low calcium pyroxene, half plag, and gabbronorites that have a mix of plagioclases and pyroxene of different calcium contents. And so what's notable about these rocks in the Mg suite is they also have a very high creep abundance. So these are samples, from the Apollo collection, so they are from these near-side procalyrium creep terrains. And they have an age range that does overlap somewhat with the Faroan anorthosites, but they are a bit younger. So these are thought to be very early intrusive volcanism. So plutonic rocks that formed within the anorthosite crust around 4.1 billion years ago and older. Most of these are, since they are intrusive rocks that they didn't erupt onto the surface, most of them are really just exposed through impact events and brought up to the surface in that way. The alkali suite is some of the weirdest rocks. They're more sodic, more alkaline plagioclase. They're creep rich for sure. So they're definitely this kind of near side procalyrium creep terrain. And they include our alkali anorthosites, norites, gabbronorites, creep basalts, which are kind of a debate. Are these actually extrusive rocks that erupted onto the surface, or are they impact melts? Were they also just brought to the surface by big impact events? And then granitic or felzite kinds of rocks. They have similar ages to the Mg suite, but they extend even a bit younger. So an example of where we find some of these potential alkali suite rocks, this is an area that wasn't sampled, but we see in remote sensing data it's really high in silica content and is thought to be a kind of granitic or felzite type composition where you have the Grutizen domes, this kind of mound here in the top and this lower one actually. These are thought to be these very ancient volcanic eruptions of these very evolved compositions, so silica rich. They're not exactly analogous to terrestrial rocks, but where you get granites on the Earth is usually at subduction zones through remelting of the crust. And so on a one-plate planet, we still don't have a great idea of how you get these very evolved compositions to form and erupt onto the surface. So this is a really fascinating area of study. The other place that you see these evolved lithologies, MG suite or the alkali suite, is within impact crater deposits. This is the Aristarchus crater on the kind of northwest near side, and it's 40 kilometers in diameter. If you look at its central peak, we can see this. This is one of my favorite pictures, these striped central peak. So the central peaks are kind of the material that, it's this little mountain that grew in a matter of minutes from the crust being compressed down by this extreme pressures of this impact event that created the Aristarchus crater. And then this crust rebounded up. So the central peaks are really exposures of the deepest material in the moon's crust. And so when you see these kinds of stripes across here, these are each different compositions. And so we think there are some really interesting evolved compositions within the Aristarchus crater. And the little bits and pieces that we have in the sample collection are probably, ejecta from craters like this.
A couple of questions.
Mm-hmm.
What would cause it to be striped vertically?
What would cause it to be striped vertically like that? So you could have a dike. You can have some kind of weird intrusive event here that has just happened to be exposed just smack dab in the middle of this crater.
Go ahead.
Yeah, go ahead. No, that's it.
From the chat box, Jeff Plate says possible hotspots from convection cells in the early mantle when the lithosphere was thin as a cause of the intrusive volcanism, I guess.
Mm-hmm. Yeah, certainly. Yeah. The question is how do you get these weird compositions that are so silica rich? You have to have had some kind of differentiating, concentrating of these elements within the magma body. So there's ideas about how you have, an intrusive event, magma rises and then kind of stalls, and then only part of that erupts. But it's I don't know, lunar magmatism and these kinds of questions that require kind of shallow bodies of magma to sit and evolve it's a hard problem to work out, and we don't really have any super great samples, just little bits and pieces that were scattered from impact events like this.
One thought that I have is that intrusive volcanism is often associated with halos of mineralization on Earth. Could this be, especially with the impact crater central peaks and so on, could we be seeing some process of segregation and concentration in the deeper crust?
Yes. Do you mean unrelated to the impact, right, and just exposed by it?
Yeah, the impact is just sampling it for us.
Mm-hmm. Yeah. I mean, that's the fantastic thing is that, we have never visited a site like this, but these craters have done this amazing job of just exposing these bizarre things from way deep down in the crust. And now they're just sitting there in the surface. You can see all these little boulders that have rolled down this central peak. All you have to do is go right up to the bottom there, pick those up, bring them back, and we can answer these questions.
Thanks.
Two more questions.
Other questions before I keep going, or?
Let's see, two more comments from chat. True could also be caused by major impacts going deep in the mantle, I guess from the remelting. And also
Okay.
for the central peaks, it could be differential weathering.
Yeah, it can. Sometimes, central peaks are areas where you have a steep slope and you have material moving down slope a lot, so you're typically usually exposing fresh material. But for this case, for Aristarchus, we have a variety of other compositional measurements that show there's silica-rich regions in here, mostly from the multispectral data, cubed, Kaguya, multiband imager, that shows we really do have a very interesting difference in composition being exposed in this case. But yeah, definitely, that's a consideration in a lot of places.
Okay, thanks.
Mm-hmm. So lunar soils, we've just talked about all these really beautiful, fascinating, pristine rock types. But then when you're at the moon, you're not looking at typically beautiful, pristine rock types. You're looking at this big, beat-up mix of things. And so this is a plot, the same kind of plagioclase, pyroxene, olivine from Lucy et al., that's showing where the lunar soils from our return samples and meteorites plot. And so none of them are up here in this perfect anorthosite that we talk a lot about because it's so interesting to understand the magma ocean. Most of them are these mixes that are the nerdic anorthosite, anorthositic norite. Down here, you're really getting into the Mare basalts. But here's our creep-rich rocks down here. So you just have this kind of broader mixing. And again, this is going back to what I talked about in terms of the regolith. And that mixing leads to a stratigraphy of the highlands that is not the kind of perfect picture that you have coming from the magma ocean theory. Where we see anorthosite on the moon is typically exposed in basin rings, within crater central peaks, and it is coming from beneath this more mafic anorthositic norite, neritic anorthosite layer. And the layer, this is the regolith, this is this mega regolith, big mixed area. And so the stratigraphy is going from kind of, a slightly more iron-rich, poorer iron, more anthracite-rich, and then into the mafic material, which is where you're getting these kinds of intrusive rocks from the MG suite, as well as getting down into just kind of a more mafic lower crust potentially, and then into the upper mantle.
Can you speculate on how many kilometers those various layers how thick that would be?
Many. I don't know off the top of my head, but the regolith, the mega regolith on the moon is kilometers thick in the highlands. And where we see anorthosite, it's being dredged up from kilometers depth often.
Okay, thanks.
And that is because of the crazy impact history of the moon. This is showing the orange circles are every crater on the moon greater than 5 kilometers in diameter, I believe. So you can see, right away, the younger areas, the lunar maria that haven't had as much time to be battered by impact events over time, because the impact flux was so high early on in the moon's history. You can see just this immense difference with the Lunar Highlands, where they really have suffered great many cataclysms. And that leads to this regolith that we're talking about, 10 meters it's up to 10 meters or so thick in the lunar maria, but well above that in the highlands. And we don't really know how thick. But the regolith is just a kind of generic term. It was originally proposed by Merrill in 1897 for a terrestrial definition. The entire mantle of unconsolidated material, whatever its nature or origin, was proposed to be called the regolith. And when that was adapted to the moon, this is the Shoemaker et al. Definition from 1967 when they were at the Surveyor 3 site. they were just said the regolith is this layer of fragmental debris of relatively low cohesion overlying a more coherent substratum. In the Mare sites, this is not so hard to understand. I mean, you have impact deposits, fragmental material, and you don't have to go down too far, maybe 3, 5, 10 meters before you hit essentially bedrock. But in the Highlands, this quote from Santala and McBride in 1995, the moon has been just so beat up, fragmented, fractured by these impact events that you don't really have a bedrock layer at any point. You're just kind of grading down into less and less fractured and beat up. So the local definition of the regolith in the Highlands is really kind of philosophical, where you're transitioning from regolith into bedrock there. And I had a thought about this that has now escaped my head, so hopefully that'll come back. But the regolith is generated from impact events of all sizes. So early on, you have these huge impact events, like the Oriental Basin shown here. It's nearly 1,000 kilometers across. Just the ejecta of that is going to become a part of the regolith. And then all the way down to very tiny impacts that are continuing to alter and even contribute to the regolith. This is a 10-ish micron crater that is caused by a micrometeoroid impact onto a single particle of soil. And so early on, the biggest contributor to the regolith in the Highlands were these big impacts, not necessarily just 1,000-kilometer, but there are a ton of 100-kilometer impacts in the Lunar Highlands. Another idea for how the regolith is kind of continuing to be produced is through thermal fatigue. You have just such extreme temperature cycles on the moon that rocks that were maybe coherent, you can see there's boulder tracks for these two rocks or boulders, rolled down a slope and came to rest, and now they seem to have just kind of fallen apart. And that might be due to this kind of extreme temperature cycling that promotes fracturing. And the bigger pieces are just kind of through either thermal fatigue or through smaller impact events constantly being worn down until you get this really fine-grained average or median particle size of around 70 microns. I really like this example. This is Mare exemplum. This is from Galt in 1970. This is not a real Mare, but an example. He produced a fake Mare and through impacts in the lab showed how a Mare surface would evolve, or this is how the original Highland surface would evolve as well. But through impact cratering, these are just subsequent after more and more impact events until you get down to really the surface is just completely saturated in impact craters.
Brett?
Mm-hmm.
This is David Kring at LPI.
Hi,
in
David.
case the students are interested, the film that Ames made with that experiment was digitized, and it's posted on the LPI website if they want to see that actually occur in a film loop.
Well, that is fantastic. I didn't know that. I've never seen the film. I would love to go see that. This is where this same paper from Galt in 1970, this is where the real definition of saturation first came in. And there's this diagram that, I don't know, it's stuck in my head. I imagine it's stuck in a lot of people's heads of the definition of the term saturation. It's essentially like if you had a closest packed, perfect set of craters, that would be saturation. Of course, this never actually happens. what you get is something called, kind of goes by various names, but the equilibrium saturation or equilibrium population of craters. And so from the same work by Galt and then expanded on in a lot of other places came this definition of equilibrium, where it's really that on average for one new crater that forms, one crater of the same size is destroyed. And this occurs way below the saturation, this geometric saturation. It occurs at around 10% of this kind of mathematical definition of saturation. And craters smaller than around 50 kilometers, there's kind of a range. It depends on a number of factors, but much of the Lunar Highlands is really in equilibrium up to these very large craters, so up to 50 kilometers or so in diameter. And what's this difference? Why is the equilibrium where craters are being destroyed at the same rate they're produced at such a low rate of, or a low fraction of the saturation? And this is another from the same paper, beautifully illustrated, of what happens. One crater doesn't simply, destroy everything in its, directly below it. These craters, through processes of known as ballistic sedimentation, but essentially the impact erosion, the ejecta that's thrown out, all of these smaller secondary craters and the debris of the impact events that scours the surface, they're really affecting a large area of the surface around each impact event. So you can see what that looks like from these craters being kind of peppered by the smaller events. And now we can see.
Quick question.
Oh, sure, go ahead.
Does this mean continued reworking at depth of both the regolith plus the bedrock down to several kilometers?
It's not continuous reworking. So there's a really good paper by that kind of goes off this early work and was redone, I think just maybe last year, from Emily Casello, and she kind of updated these models of how deep the regolith is being reworked, or how frequently it is being reworked at different depths. So, so the uppermost surface is just being turned over. The upper couple centimeters is just being turned over on a scale of like 100,000 years or so. It's being completely turned over. But at greater depths, that it's you can get differences because cratering is so random. But at greater depths, it might have only been overturned once or twice, and that's what you're seeing more at. At a kilometer depth, you're going to have something that is not been exposed at the surface and reworked in that way. But that is a good question for what is going on here in this upper regolith. One of the things from LROC that we've been doing is looking at these new craters. So you're seeing an image from essentially a before image and an after image. We spend a lot of our time just re-imaging the boring, bland parts at the same exact illumination conditions so that we can look for new features. In this case, what's changed between the time that these two images were acquired is a new 12-meter or 40-foot impact crater. And so you can see the crater itself right here in the middle. And then hopefully you can see too these rays essentially that, they're very subtle. If you didn't see the difference, you might not see these rays, but they're stretching out really far from this tiny 12-meter crater. And that is because these craters are really affecting the surface. This 12-meter crater has caused surface changes nearly 2 kilometers away from the crater itself. So back in the, the Galt days, there was a definite appreciation for the reworking of the regolith, but we're now finding from these new observations that reworking is actually 100 times faster than it was originally thought. And to really emphasize how far these surface changes are going out, this is a ratio of the before and after image, so you can see the changes highlighted. We also, this is not a
Question
new.
real quick.
Oh, sure, go ahead.
Go back to the last slide.
Mm-hmm.
Why isn't it like even everywhere in all directions?
You mean why is there kind of an asymmetry in the ray pattern?
Yeah.
Okay. So this is probably likely an oblique impact.
Okay.
So you can see this kind of. Well, actually, I should check that. Well, actually, there's two reasons here. You do get asymmetry when you have an oblique impact. It usually has to be, the impact coming in pretty low to the horizon before you get really strong asymmetry. But this could be related to, the impact would have been coming in. The impact door would have been coming in from the east here. But if you go to this slide as well, where you can see just the general surface better, you can see an ancient or a really degraded crater here, and the topography is likely blocking some of the. You can actually see it. I've never really thought about this part before. This is a great question. You can see that some of these rays are kind of going right to the edge of this crater, and that's fantastic info because it's showing us that a lot of the ejecta is coming out at really low angles. We even see places where there's a really small topographic obstacle, like a block or something, and you can see where the rays have kind of got blocked right by that rock and but continued on either side of it.
Thank you.
Thanks.
Other questions right now?
There's a couple on the chat box. So just, does this mean, are there published time curves for the reworking, both the angle and potential shielding by something at the crater lip?
Okay, I think I heard two separate things. Yeah, there's published curves of the reworking and the models for the depth of reworking of the regolith. The best is that Costello paper that I can look up the reference for you after this, but it was published in the last couple of years. And then what was the second part? Something about shielding?
It's, both the angle and the potential shielding by something like a ridge or crater lip.
That could lead to the asymmetry.
That could lead to the asymmetry, yes. So,
Okay, yeah.
comment. Anyway, thanks. Go,
Okay.
and we'll continue on.
Okay. I wanted to show this image because this is it's a young crater. We think it must have formed in the last 100,000 years, based on its appearance. It's like strikingly fresh. It looks like it's formed yesterday. Also, it has some thermal properties that the diviner instrument sees that suggest the regolith here hasn't been reworked, it hasn't been reworked through this kind of micrometeoroid bombardment process. This is, oh gosh, I've forgotten how big this crater is now. It's something like 40 meters, or no, I think it's, all right, about it. It's 1.2 kilometers. This is, I think it has a name now, but we've been referring to it as Chappie because it's on the rim of a larger crater, Chaplagan. And you can, the last crater, it's really cool that you can see exactly what's changed, but it's hard to, we barely have resolved the crater itself. And then this one, you can just see how the impact process is really working to affect and scour the regolith surrounding it. You can see where it's kind of gone in and out, essentially like flowed over the surface. And this is another view of the same ejecta deposit, but looking straight down at this. And it's just really remarkable. It looks like it's still moving or something, but you can see this process of kind of scouring and reworking of the regolith near craters. And now we know it's not just where you can see easily, but these craters are affecting the surface very far away. And so if you scale this up, that was a 1 kilometer crater, and now here's a 1,000 kilometer impact event resulting in the Oriental Basin. The Oriental Basin here is where the arrow is pointing. Heather Meyer has mapped out all of these light plains deposits surrounding this impact event. And so we think these light plains deposits are similar to what was seen at the Apollo 16 landing site, a kind of ejecta and reworked local material that kind of pond in lows around impact events. And you can really start to see how seriously the Highlands regolith has been altered by impact events and mixed by impact events that are just really near global in their scale, at the very least hemispherical in some of these big impact event cases.
One more question.
So in terms of saturation, do you consider like lofting as well of the ejecta and like maybe like how much ejecta kind of stays in like a temporary orbit and then lands like in a completely different location?
Yes. Well, I would have to say I don't think the models probably include that. But yeah, some of the ejecta is definitely going to exceed the escape velocity. We do see deposits or features related to impact events at the antipodes of some big basins, and I should have included this. We see impact melt deposits in the Lunar Highlands at the antipode of Tycho crater. So Tycho's on the near side. We see these little fresh impact melt deposits on the exact opposite hemisphere of the moon from Tycho that, not conclusive, but may have been impact melt that has essentially been deposited on the other side of the moon from this 100-kilometer impact event. So while there is definitely evidence that that some of this material is going much farther than the models kind of consider, I don't think that most of the models actually include things like that. There was a recent paper looking at the really early kinds of big impact events and how the crater population would have been affected by that kind of material raining back down, but I would have to look that one up and send that to you if you're interested.
Okay,
Well, thanks.
thank you.
Okay, so yes, going back to this really simple diagram that I think is nice and just kind of explains a lot from Hawk et al. In 2003. Just I think now that we've talked about kind of the impact process, the mixing, can get a sense of why you have this kind of mix of material from all over the moon, from different depths, that kind of ends up as our regolith and megaregolith, which I think I've said a couple times but not defined. The megaregolith is just the stuff that is, probably kilometers thick in the highlands and is largely that kind of earliest debris that was produced by impact basins, mostly.
Another question from the chat box from Hunter. Are the observations of small recent craters on the moon being used to update the NEA population statistics? For the 12-meter example, how big was the impactor? I would assume that a meter or less, this would be below NEA observation abilities of our current generation of instruments.
Um, well, I don't know about the observation part, but the statistics for these small craters are kind of just starting to get to the place where we can do something with them. The initial work that was published by Spire et al., I believe in 2016, gosh, time flies, that looked at this population of these craters, these new craters, I think included about 200 impact events. And those range from, in that case, I think the largest was tens of meters down to essentially, where we can just barely resolve a crater. And then there's tons more that we cannot resolve. We just see a surface change. We can't measure an impact crater to kind of understand the impactor itself.
If I could interject.
Okay.
This is David Kring at the LPI. The other thing that's important to understand with regard to that question is there is a range of scaling formula for calculating the projectile size from the crater dimensions. And it appears that the correct scaling relationship to use is the one developed by Keith Holsapple. That was determined based on one of these small craters for which the energy was observed by the Marshall Space Flight Center's impact flash experiment. So it's, as you said, we need more events to have better statistics, but the other part of that is having a reliable scaling relationship.
Yeah, and people are definitely proposing instruments that would get a better handle on the impact flashes, so the energy released in these impact events by monitoring the moon from potentially like the gateway or something like that. But I was going to say the number of craters now detected is something I believe it's well over 500. We're, I think, over 800 now. And so we're starting to get to a place where we can really dig into the statistics of these. We also have started to see some bigger impact craters. Like I think the biggest one that we've seen now is 70 meters in diameter. So I think this is a place where you just need to stay tuned. LRO has been in orbit for 10 years. And with these kind of additional years of the mission, this is one of our important measurements that we continue to try to improve. One other paper I just wanted to highlight because I think it's so fascinating, just in terms of understanding what your regolith is made of when you have, we go to a specific site and what are you gonna find there? You will definitely be finding things from far, far away. We talked about, the kind of hemispherical nature of some of these basin forming impact events, but there's been some cool modeling on this, how just every crater is giving this heterogeneous distribution because of the way that the rays form. So the Apollo 12 landing site was very far away from the Copernicus crater, but it was on a ray of Copernicus. And some of the, we think, well, you can see actually in their key points, they support provenance of the Copernicus provenance for some of the material that was collected at the Apollo 12 landing site, even though it was so far away. So even when you are very far very far from a Mare deposit, you can still have a Mare or laterally transported component of the regolith from pretty great distances, and it will not be uniform. There's definitely a randomness to this, depending on where within the array you might or might not fall. I think we are getting towards the time that I was supposed to cover, so I just will go quickly through a last bit about the polar regolith, the polar highlands, because that was on my list of assigned topics to cover. And so briefly, we do have a hard time measuring the composition at the poles by reflectance spectroscopy because it's always very high incidence angles, shadows, hard to see. But the laser altimeter, LOLA, on the LRO spacecraft, they found a way to get not just topography information, but they can look at the amount of light, the percent of light that their laser emits that is transmitted back, and so get a reflectance measurement of the surface that is based on their own provided light, not the sunlight. So this is from Lemelin et al. 2016, and you can see the reflectance of the near side, very familiar looking. But what is quite different from what we normally see is the South Pole here. This is I'm just taking the moon and now tilting it on its side to look at the South Pole from this LOLA reflectance data. And so you can see here, this is probably going out to, I don't know, 50 some latitude. So these are, our PSRs and our permanently shadowed regions. But this is essentially the same composition as the rest of the highlands, probably. You can see part of the South Pole Aitken Basin. Likely there's some South Pole Aitken Basin material near the poles. But you have essentially highlands regolith, and sampling this material would be exciting because it would be our farthest away from the Procolarum creep terrain. And yeah, so I guess I forget what my specific point I was making by putting this here now, but we're just going to be sampling the same kind of anorthositic norite or noritic anorthosite material at the poles probably. Of course, it has experienced a different history. The regolith within the permanently shadowed regions has certainly been a lot less weathered by the solar wind. It's harder for the solar wind to make it in there. And, of course, you'll have whole classes I hear about ices and things, so we won't get into that. But the base material is going to be this, this kind of highlands material. This is Malapert Mountain near the South Pole, just to give you a pretty view of what the highlands look like near the poles. These areas that experience a lot of illumination, surrounded by a lot of shadows. And David Kring, since you're on, you'll like this. This is from an email that David sent out yesterday highlighting a paper that is now in press from Sargent et al., where they are trying to understand the nature of the regolith within permanently shadowed regions. Of course, if you're going to be mining ices, this would be an important consideration. What are the geotechnical properties of the regolith like there? Are you going to be just hitting cement right away? And so we have these natural areas where you have boulder tracks. This was done at Apollo sites too, looking at boulder tracks. How far does a boulder that's rolled or kind of pops along the surface in this case, how far does it press down into the surface? And this work from Sargent et al. 2020 shows that even when this boulder has gone across into a permanently shadowed region, it looks like it's still just hitting the same kind of regolith, similar to equatorial regions on the moon. So at least in the
A couple
area,
of quick questions.
not enormously different.
So from Jeff, has there been any work on diagenesis for sedimentary rock deposits?
Sedimentary rock deposits on the moon. So are you talking about just kind of within the regolith?
I think it's diagenesis of the regolith.
Yes. Yeah, I mean, if we're looking at kind of depth through the regolith, we are, the data we have include, looking at what impact craters exposed, and also there were cores, the deep drill cores that went sampled down to 3 meters. So we can look in that extent and see that, the regolith is kind of just this random mishmash of ejecta deposits interspersed with, more mature material, fresh material. Generally, as you go down, you see fresher, less weathered, less exposed material, but the regolith is really just beaten up and mixed up, and that is something that I would love to see more work on, actually.
Yeah, and I think the story here is that the diagenic process is really one of impact rewelding of this clastic material.
Right, yeah, because craters don't just, create regoliths, they also create new blocks and blocky materials, and that's all the breccias that we see. So,
Yeah, and we have a bunch of samples of those. The other question was, I was wondering how the 3D images of the moon were taken.
The topography data, or so there's a couple answers. I mean, topography, the elevations we get from the laser altimeter, but we also have 100-meter stereo data, 100-meter topography derived from stereo data that comes from the Lunar Reconnaissance Orbiter camera, wide-angle camera. And so it just has such a wide field of view that you get overlapping images at different look angles and can kind of reconstruct topography that way. Another way is with the LROC narrow angle camera, we get stereo images at very high resolutions where you can get 2 to 5 meter per pixel digital terrain models derived from, we usually do 3 look angles, slew the spacecraft over, look down at the surface, get a nadir image looking straight down, and then on the next orbit over, slew again to look back at that, and so construct, you can get topography in stereo in that way.
Okay, thanks.
I think that's all I had here. My last slide is the resource potential of highland soils, which Dan had asked me to talk about, and I thought maybe there was something I was missing, so I emailed him and asked, what are you talking about, resource potential? Can I read something? But yeah, he confirms actually there's little beyond, the kind of typical oxygen extraction from the soils and just construction materials. Of course, the polar highlands regolith is a different story, but in terms of the anorthositic regolith, it's not going to be full of ilmenite or titanium or a lot of mafic iron-bearing minerals. So probably some of you know more about this topic than I, but I will leave this here. And I think that's all I had. So more questions.
Yay, well, thank you.
My pleasure.
The mic is open for questions on the table, and also I invite more questions from the chat box.
There's been 2 questions in the chat box.
Okay. From John Gruner, I'm guessing the lunar polar regolith would have much less basaltic and creep components than the Apollo 16 regolith. Yes.
Hi, John Gruner. That's funny. You should ask. Yes, I think that you would Highlands or Apollo 16. It's right smack dab in the middle of the near side Mare basalt surrounding. So I think you would have a bit higher Mare basalt contamination there than you would at the poles. But there is this kind of distal transport. So you're still going to have stuff thrown in from quite far away. But it takes a bigger crater to get that far. So it's going to be rarer. So overall, I think, the Apollo 16 soil as an analog for composition of polar regolith is kind of an upper end number.
Can we quantify this?
Now I don't have to email you back, John Gruner.
Following that up, can we quantify this by looking at the felspathic meteorites in the lunar meteorite?
I don't think so, really, because the meteorites, they are regolith. There are some regolith breccias, but we don't know that, and probably not. They're probably not sampling this kind of majority of material from the upper surface. And, we're talking about the mixing and things where that's really most happening in the upper, few meters to tens of meters, really. And so these impact events are mostly sampling way deep into the soil, into the surface. So I think that would actually be kind of the other end member, maybe, for what the polar regolith would be like.
Terry Trevino says, can we build shelters in these highlands?
Yes. I don't know. Yes. I mean, the highlands, so if you're talking about kind of what the physical nature of the highlands, the regolith is definitely thicker. And when you're on steeper slopes, you'll have more fragmental material moving around. But on a, kind of flattish highlands area, you are not really going to be that different from the mare. In fact, you'll have a bit of an easier time because the highlands are less blocky. You're going to run into less large blocks.
Rob Mueller comments on that. In terms of construction materials, are the geotechnical properties of highlands regolith unique?
I'm not an expert in this area, but maybe Dan, you are. I think no. I don't think they're extremely different. You have the same basic things, I guess plagioclase can break down a bit easier, but you're still anywhere in the highlands or mare going to have around 50% agglutinates, glass, these same kinds of grain sizes. The highlands are older, but you reach a kind of equilibrium state pretty quickly. The particle size distribution, it can't get smaller because particles start welding back together through impact melts. So overall, I think the Mare Highlands geotechnical properties are about the same.
Yeah, I don't think it would be.
That's my non-expert answer.
I don't think it'd be hugely different either. See, another question, where are the majority of lava tubes located? Wouldn't that be the best place for shelter?
Okay. We see pits, and I think that is probably what you're talking about with the lava tubes. Lava tubes are forming in the Maria. There's no lava tubes in the highlands. We see a few pits that are forming in fresh impact craters in the highlands where impact melt has drained away. Since this is the highlands, I guess, since we're only talking about the highlands, yeah, it's not in the highlands. And if you want my own opinion on whether those are the best place for shelter, sure, you're going to be sheltered pretty well from, solar winds, radiation, impact events, but you also are going to be down in a hole. So that's not very fun.
Okay. More questions from the table?
My question's about this last slide. Is there when you said like the poles could be a different story and something we really got to look into, do you think there's some resource potential with like volatiles in the poles and like the ices there? I guess I'm thinking of like the PSRs. Maybe I'm making a really bad connection.
We're actually going to have a whole lecture on that.
Okay.
But
Yeah, I only touched on that because, that is such a huge topic that people are very, very, interested in. And so when we're talking about, I guess when I'm talking about highland soils, I mean like not within the permanently shadowed regions. That's a special case where you might have ices. We know there are some ices, and that is a different kind of resource potential than just from the rocks themselves, which is all I'm covering today.
Okay, definitely. That makes a lot of sense. Thank you.
Of course.
I have a thought about the essentially the basaltic or the mafic layering, the serial cooling during the magma ocean event. So as you get farther down into the anorthositic crust, would you expect some sort of odd magma fluid interaction toward the base of the crust to produce some concentration of mineralization?
I mean, yeah, the magma ocean story that I tried not to give you, but still gave you a little bit of, was, vastly oversimplified. There's all kinds of questions of, how much of the moon was molten? Is it really flotation or is it serial magmatism? There's a lot more to that story, a lot of open questions. But the kind of basic hypothesis is, holds together still. And so, yes.
I thought your image of the various units on that central peak, Crater Central Peak, really spoke to the fact that there's stratigraphic data to be had in looking at essentially crater peaks and crater rims.
Oh yeah, that's been a huge topic. There have been numerous papers from, I'm going to forget the first one, but there's some Cahill papers. I can't remember her name, for who published kind of the first general survey of these craters, but looking at the compositions of these peaks. And it is complex with the data that we have, but yeah, that's another way to look at the kind of the overall stratification of the crust, and that's where you do start to see some of these complications of different types of materials being exposed at depths, and why isn't there more pure plagioclase deposits? And yeah,
From Rob
definitely hitting on the complexities.
Yeah. From Rob Mueller, can you comment on the scale of the topography at the poles? I think it is underappreciated how extreme this terrain is.
Oh, okay. So I think the opposite, actually. I think the terrain at the poles looks very extreme because you're always seeing it in really large shadows when the sun's low on the horizon. It really emphasizes the differences in elevation. But really, it is absolutely no different than the rest of the Highlands. It's anywhere kind of same slopes of, you have, like Shackleton crater, definitely steep, relatively fresh crater, so it would be hard to get down in there. But a lot of the more, a lot of the craters are just, the more typical kind of degraded craters where the slopes generally shallow to, less than 10 degrees. So no, I don't think the slopes are of extra concern there.
Okay, Rob is following up. On a human scale, are these large mountains and valleys, correct?
Yes, I mean, it depends on, I'm not sure what these, so it depends on what we're talking about. But yeah, the crater, I mean, there's kilometers worth of topography for sure. So there's like Malpert Mountain, it's a couple kilometers tall, I think. But it's not like, it's still kind of a shallow slope overall up to it, definitely less than 30 degrees.
So what I hear you saying is that the terrain around the poles is not all that dissimilar from the average of any highland zone.
Exactly. It's the same.
Let's see, from Terry Trevino, the regolith particles seem as if they would cause fabric/exothermal coverings to decay rapidly. Are the microparticles sharp?
Yes. Because of the way they're produced, no kind of erosion processes like on the Earth that round particles through wind, water. The lunar soil is pretty angular, subangular technically. But yeah, it's very abrasive. It does wear down materials. There's images of some of the Apollo suits looking at, wear to fabric, wear to materials. You can see like the surveyor, Apollo 12 landed near one of the surveyors, robotic landers, and they were able to go take, pieces of that spacecraft back and look at how the landing that would have caused a lot of ballistic trajectories of dust and kind of scoured that spacecraft. You can see how it affected the materials. So, yes. So, I mean, the lunar soils, the dust, they're definitely abrasive.
Okay, from John Gruner, Rob, take a look at the slope maps at the LPI South Pole Atlas. Plenty of areas of less than 10% slope. I meant to type 10 to 15% slope, all within the Apollo experience.
Yep.
More questions from around the table?
I have one.
Okay.
So feel free to correct me if I'm wrong on this, because I might have misheard. Has the Lunar Reconnaissance Orbiter detected 800 impacts?
Oh, something like that. That hasn't been published yet. Kind of working on another big catalog of those before to get some really good statistics. But so don't quote me on this, but yeah, it's somewhere in that order.
So do we think that lines up with about the same flux we find on the Earth for impacts as well?
Oh, well, the Earth, a lot of what we're seeing are really small impactors that would have broken up in Earth's atmosphere. Yeah, so the Earth Moon experienced about the same impact flux. And what we have seen so far actually lines up pretty closely with the impactor population that was expected and modeled. The first publication, I think it was about a third lower impact flux than would have been predicted, but that was out of 200 craters that were detected at that point. So that's why we're working to update.
Thank you.
More questions? Well, I think we've forced Brett to work pretty hard this morning overall. So I just want to give you a thanks and another round of applause.
Yeah, my pleasure. It was really fun. Good questions.
It was awesome. Thank you very much.
Thank you.
Thank you.